All right, hello, Algebra 2 kids. Welcome back to some math. We're going to be talking here about radical functions. Okay, we've talked a little bit about these, especially when we were doing those quadratic formula problems, right? Those have to deal with radicals. But we're just going to do a quick review of what a radical is. We're going to simplify some, and then we'll get into some tougher stuff where we actually like add and subtract and multiply all those. Okay, so start with the basics, and then we'll go from there. Okay. So again, just talking about these, we have, right, our kind of our standard radical. Again, when we say radical, that just means this symbol, kind of this check mark, like almost like long division sign symbol. Okay, that's actually what the radical is. So usually when you think radical, you think square root, right? That's kind of our most common radical that we use, right? But there's other types as well. We can have a cube root, right? And you see that by the number that's here, and that number is called the index. Okay, so whatever the index is kind of tells you what type of root that you're taking. Okay, so you can have a cube root, you can have a fourth root, you can have fifth root, sixth root, seventh root. We don't see those higher ones as much, but yeah, you can have all types of ones. These are the types we're going to be seeing here in Algebra 2, so just wanted to lay those out. So the index is this number, the radical is the actual symbol, and then what's inside the radical, the fancy name for that is the radicand. Okay, the radicand is just whatever is inside of the radical. Okay, so just some vocabulary there for you. Okay, and what's going to be important to you guys as you learn these, as we simplify these radicals, is it's really helpful. It's not necessary, but it's really, really, really helpful if you know and kind of keep in mind these perfect squares, right? Perfect squares, right? That means, right, I have them all listed out here, right? But how you know they're perfect squares, right? So 1 squared would equal 1, right? 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on, right? When you multiply a number times itself, there's the first 10 of them at least, okay? There, the list goes on. But in the perfect cubes as well, these are also helpful to know. Okay, obviously these numbers are bigger because it's like 1 cubed. 1 times 1 times 1 would be 1 still. 2 cubed, or 2 times 2 times 2 would be 8. 3 times 3 times 3, or 3 cubed is 27, and so on. So we have our perfect cubes. We do have perfect fourths as well. We won't, again, not as important that we list all those out, but it's really, really helpful, okay, especially as we simplify some of these. If you know these perfect squares and keep them in mind, it saves you a lot of time and it makes simplifying a radical a lot easier, okay? So there's the basics, okay? Now, getting into simplifying these, again, we're starting very easy, something you would have seen definitely in Algebra 1 or earlier. But if we simplify these, right, what it means is we actually take the square root of the cube root or the fourth root and get our answer down to either a single number or just kind of like a fraction. Sometimes we can't simplify it all the way, but just reduce it as much as we can. Okay, so like if we look at number 1, we're asked the square root of 49. You guys probably know this. This is asking like what times itself equals 49. And so the square root of 49 would equal 7. So that's an easy one. Looking at number 2, we think cube root, right? We know it's a cube root from this 3 index, okay? So the cube root of 64, again, thinking about our list of perfect cubes, 1, 8, 27, 64, right? So 4 cubed, or 4 times 4 times 4, would equal 64, okay? So the cube root of 64 would be 4, okay? Number 3 there, the fourth root, right? This 4 index, fourth root of 16. Okay, again, so we're wondering what times itself times itself times itself equals 16, and that would just be 2. If you did 2 times 2 times 2 times 2, you would get 16. So reversing that, the fourth root of 16 would be 2. Okay, so there's just some basic problems with just the number as the radicand. Okay, now when we include some ones with variables inside, it doesn't get too much harder, but what I like to do is I kind of like to almost, when I do this, I like to almost separate it in my mind. And I think, okay, square root of 16, square root of x squared, and do it almost separately. This is, you wouldn't write this, but this is kind of how you think about it, okay? So the square root of 16, okay, so the square root of 16 would be 4, right? 4 times 4 is 16, and that's just a normal square root. But then the square root of x squared. And so for this one too, we're thinking, okay, what times itself would equal x squared? And that's easy, right? Something times itself equals x squared. we could just say x, right? X. Number 5, the cube root of 27, xy cubed. Okay, so again, thinking about this, what can be helpful is break it up, at least in your mind, break it up. Square root of cube root of 27, cube root of x. And right, even the x and y there, they kind of look lumped together, but we can even separate those, right? So the cube root of 27, cube root of x, cube root of y cubed. Okay, so the cube root of 27, again, 27 is one of my perfect cubes, right? So that's going to simplify down to just 3. Okay, cube root of 27 is 3. Cube root of just a single x. Okay, now this x does not have does not have an exponent with it. Okay, so we're not going to be able to reduce this down at all. So I'll kind of deal with that one at the end. But just moving on to the y's, cube root of y cubed. Basically, if the exponent is the same or more than the index, we're going to be able to simplify at least part of it. Okay, so the 3 index with the 3 here means the cube root of y cubed is just going to be just a single y. Kind of the cube root and the cube kind of cancel each other out. So I was able to take the cube root of these two and get 3y. But again, this cube root of x does not simplify. There's not enough x's in here to be able to reduce that or cancel that. So that remains the cube root of x. Okay. And so we have these sometimes, some of these like almost, I know they're not called mixed numbers, but it's a combination of a normal part, not under a radical, and then a part with a radical. So we could say this is 3y times the cube root of x, okay? So that definitely happens sometimes where you have part of the number outside of the radical, part of it inside. That definitely happens, okay? Everything doesn't always reduce nice and neatly. But I hope you at least get the idea with simplifying these problems using square roots, cube roots, and fourth roots. Okay, so let me erase and we'll deal with some tougher ones. Okay, I got 4 more problems up here where we're dealing with some more complicated radicals, okay, but we can handle them, no problem. Okay, so number 6, square root of 72x cubed. Okay, so again, as you look, again, this is super helpful to have your list of perfect squares, right? Because 72 has a lot of factors, and it might be one that you might mistakenly think, oh yeah, that's a perfect square, but it's not on our list of perfect squares, unfortunately. So we can't just say like the square root of 72 is this whole number. Like if you did the square root of 72, you'd get like 8.4 something or 8.5 something. And we don't want the decimal answer, okay? So we're gonna have to do something where we, again, simplify or reduce this radical part. So again, what we can do is just kind of break it up. Square root of 72, square root of x cubed. Okay, we can kind of separate these. And whichever one is easier for you to kind of simplify first, right? This, like, I like dealing with the x's first sometimes because, like, I know I'm gonna have to do some work to simplify this. So just getting this one done out of the way first can help. So x cubed, right? Again, so if what can be helpful too is x cubed, separate it, x times x times x, right? And you might remember I showed a simplifying radicals video earlier in the year. And again, what we want, after we kind of break up our number all the way, and in this case it's our variable, our letter, what we want is pairs of the same thing. And if we have a pair of the same term or same number, that can come out of the radical, okay? This would be like taking the square root of x squared, and then this other x kind of stays in there. So an x comes out of the radical from this pair, and then this single x stays in the radical, okay? So x times the square root of x is what just the variable part reduces down to, okay? But then square root of 72, okay, think about this. Again, it's not a perfect square. It's not in my list of perfect squares. So again, I showed you guys 2 strategies to simplify these radicals as well, okay? My favorite, and again, this is, if you know your perfect squares really well, it's a lot quicker, okay? So you think 72, and you think, okay, out of the perfect squares, what are some factors of 72? Like which of these perfect squares multiplies to get 72? Okay, like a perfect square times something else equals 72. So you could say, okay, 4 times something is 72, okay? But you want the biggest one possible, right? 9 times 8 is 72, so that works. You keep going down, 16, 25, 36 times 2, right? Even if you cut 72 in half, you'll get 36, right? So that is the biggest one, okay? Usually that's awesome. If you divide the number by 2 or by 3 and you get a perfect square answer, that's the ticket. That's great. So we could separate this into the square root of 2 times the square root of 36. Okay, again, that's totally legal because 72 is equal to that. The square root of 72 is equal to that. And what I can do is I can take the square root of my actual perfect square, this 36, and that, right, the square root of 36 would just be a normal 6, right? I can take the square root of the perfect square part, but then the square root of 2, again, that doesn't simplify, that's not a perfect square, so I would leave that in the radical. But again, now that I have this kind of, and I know this is a lot of different terms, but this is kind of what I have right now, is a 6 times the square root of 2 times x times the square root of x. Okay, it's all one big group. And so what I can do as my last step, kind of recombine everything, bring together my terms outside of the group right here, so 6x, and then bring together my terms inside of the group in one radical, 2x. Okay, so this would be my final answer, 6x times the square root of 2x. Okay, so that would be simplifying that first one. Okay, now I said there's another strategy to do this. If you're not as good and it might take you a while to think about your perfect square factors like I did here, you can make your factor tree as well. So what we can do, again, it still helps, no matter what strategy you use, it still helps to kind of break it up into the number. And then for this one, it doesn't really matter. You can keep your variables together. You can separate your variables, whatever. So again, let me deal with my variables first because that takes a little quicker, okay? So again, what I like to do with my variables is expand it. Okay, I like to do that. So x squared would be x times x, and then y to the fourth would be 4y's. Y times y, y times y. Now think about this. With a cube root, okay, with a cube root, think about this. I need groups of 3 to be able to pull it out of the radical. Okay, with a square root, I only need groups of 2 of the same thing to pull it out. But in a cube root, I need groups of 3. Okay, so with my x's, right, with my x's, I don't have a group of 3, unfortunately. I only have a group of 2. So I'm not going to be able to simplify this x squared part. So that x squared is going to stay in the radical as my final answer. But with my y's, right, I have 4 y's, but I have a group of 3, right? I have a group of 3 y's right there. So that group of 3 is able to come out of the radical as a y, okay? But then all those other variables that aren't part of the thing that came out, those stay inside. So what's inside is this x times x, or x squared, y. That stays in the radical, okay? So that's simplifying my variable part of it, okay? A y outside and these left inside. And now the other strategy with breaking down this number, right? Again, if you look at your list of perfect squares, 24 isn't in there. We're really close with 25, but 24 is not in there. So again, the other strategy, if this doesn't make sense to you, it would be breaking it down into a factor tree, okay? And again, that's just kind of thinking like what times what. Any pair works of just any pairs that multiply to get 24. And so you'd think, okay, 2 times 12, that equals 24, right? And then you think about those two numbers and you think, okay, can I break either of those down into smaller factors? So you break down 2, or you can't break down 2, so you circle that. And then 12, right? You break down 12 into, right, what times what is 12? You could say 2 times 6, right? And then you just look at those two numbers. 2 can't break down anymore. 6 can break down into 2 times 3, right? And then these two are both prime numbers, so you can circle those, right? So out of my group here, I have square root of 24 is 2 times 2 times 2 times 3. So 2 times 2 times 2 times 3 is 24, okay? And again, same idea. I want groups of 3 to be able to pull it out of the radical. And I have that here, right? I have 3 2's, right? I have 3 2's. And so that 3 2's can come out of the radical as a 2, and then that 3 doesn't have a triple to come out with, so that 3 stays in the radical, okay? So 2 times the square root of 3, and then this variable part. So combining that, all right, my final answer up here, combining that, again, the outside terms are together, so that 2y is together, and then what's inside the radical is this square root of 3, and then this x squared y is also in the radical. So that, again, that's a messy one, but that is all that is left in the radical. Okay, you can simplify it a little bit, but not a whole lot. All right, so now thinking about number 8, we have the fourth root of x to the 12th, y to the 20th. Okay, now this one can be a lot, okay, but you got a ton of x's and y's in this radical, okay? But think about this, it's a fourth root, okay? So I'll show you a little shortcut when you do have big variables like this, okay? With the 4 index, right, what I would need if I would expand it would be groups of 4, right? So if I wrote out all my 12 x's and all my 20 y's, I would want groups of 4 to be able to pull it out of the radical, okay? But some of you guys, again, it helps to be good with your times tables here. You might notice that, oh, 12 and 20, those are both divisible by 4, right? Or 4 is a factor of both 12 and 20. Okay, so what you could do as a shortcut is divide both of your exponents here by the index. Okay, so 12 divided by 4 would be 3, and so 20 divided by 4 would be 5. Okay, so that's how many if you did write out all of your x's and all of your y's, that's how many groups of 4 you would have. You'd have 3 groups of x's, 5 groups of y's. So that's how many of each of those variables I'm going to be able to pull out of this. Okay, so actually my final answer to this is going to be x cubed with the 3 exponent, because again, that's how many groups, and then 5 y's, or y to the 5th. So it is really helpful when the index is divisible here. But like sometimes it's not. Maybe you have a 13 here instead of a 12. In that case, you could still pull out 3 x's, x groups, but you'd still have an x left in the group there after. But it's really helpful when the index divides evenly into your exponents there, and it creates this nice and neat group. Okay. Last problem here, number 9. Now this one might look weird. You might look at that at first and think, a negative radical. We can't do that, okay? But there is something special that happens here. Okay, so think about this. Cube root of negative 27, x to the 6th, okay? Now let's deal with this variable first. X to the 6th, okay, again, look at my index. My index is 3. 3 and 6, right? 6 is divisible by 3. So I could do, okay, the cube root of x to the 6th, right? If I divided 6 divided by 3, I would get 2, right? There'd be 2 groups of 3 x's if I expanded all that out that I'd be able to pull out of the radical. So the cube root of x to the 6th would just be x squared. Works out really nice. Okay, now the cube root of negative 27. Okay, dealing with that part. Could, like, if I asked you, what times itself equaled negative 27, okay? If you just said, like, with a square root, if I asked you, like, what times itself equals negative 16 or something, you couldn't answer that, because negative 4 times negative 4 would still equal positive 16, and 4 times 4 would equal positive 16. So there's no way when you just multiply something times itself, like there's 2 of those, you can't get a negative answer. But consider this. What would negative 3 times negative 3 times negative 3? If you did that, what would that multiply to give you? Think about this. That's negative 3 times itself 3 times, or negative 3 cubed, right? And so if I did just these first two, negative 3 times negative 3, if I just did those two, I would get a positive 9, right? But then if I bring down this third one, what's 9 times this negative 3? Negative 27, right? So with cube roots, when you have an odd number index, you are able to take a radical of a negative, okay? And it would just be whatever negative number that is, okay? So the cube root of negative 27 would be just negative 3, okay? So that works out pretty nice. So that's all I'm going to do in this one, just simplifying a whole bunch of these radicals with some variables and some negatives and all kinds of stuff. But hope that made sense. Thanks for following.